speaking on the number of K4 saturated edge.
Thank you. First, I would like to thank the organizer for very nice conference. I would like to thank everyone to be here. So today I'm going to talk about the number of K4 saturating edges. Presentation I will explain shortly. And this is joint work with my advisor, Jozsi. So first, just to refresh on the same page, the definition, the Turan number, or sometimes called extreme number of the graph, denoted by Ex, M, comma, H. Basically, the maximum size of the subgraph of the complete graph does not contain H as a subgraph, not necessarily inducing. So, as Jane already mentioned, Mantel's theorem, basically a word in this language says extreme number of a triangle is n squared over 4, and this is best possible considering the balanced bipartite graph, who is n over 2 on each side. And this is considered as one of the starting point of extremal graph theory, and later on this Turan theorem and a lot of theorems coming up. So I would like to rephrase Mantel theorem in this language. Later on we will see the connection, why we do this. So if we restate Mantel theorem, basically says if a graph of n vertices has more, even one more than n squared over 4 edges, then necessarily this graph contains a triangle. And later on, Rademacher has a published result. Says not only when you have one more than this extremal number, not only you have one triangle, but you all of a sudden has n over 2 triangles. So there's this sudden jump from no triangle guaranteed when you have n squared over 4 edges to when you have one more edges, you have all of a sudden linear remaining, in particular n over 2. And this is best possible if you just consider this, again, balanced bipartite graph, n over 2 on each side. So I will skip the ceiling and the lower side and just add one edge on one side. So as you can see, the only triangle comes from this edge with any vertices from the left-hand side, any vertices from the left-hand side. So Erdős later extend this result and says when we have q additional edges, when you go beyond this extremal number, then actually each additional edge will give you n over 2 additional triangles. And this is, of course, again, best possible in the sense that if you consider this graph just adding matchings, okay? Each additional edge gives you n over 2. So this is sharp, as observed by this example, and this is, you cannot do better. And this q is linear for some small constant times n. And it was conjectured by Erdős and been open for 20 years that the constant c here can be taken as 1 over 2. And it's a long-standing conjecture proved by Lovac and Shimonovich in '83. And also, this works before this one. Erdős also showed the analog result for larger cliques, not just triangles. So basically, he says if we define the Turan number for the cliques, when you have one more than the extremal number, then all of a sudden we have many, many cliques, not just one. Okay? An example, as one might guess, I will just draw one for K4 case. Then the best possible example, as one might guess, is the most natural one, adding one edge into a Turan. And recently, Drew Mubai extended their result to colored vertical graphs and some small height graphs. Okay? And the same example for colored vertical graphs. Just adding one single edge in the Turan graph. So, so we can define this Erdős-Rademacher type problem in the following way. We say a problem is Erdős-Rademacher type, then we can do the following. You can grab the extremal question and says, what's the number of forbidden configurations you can have when the graph is somewhat denser? In the previous example, the denser is in very weak sense by Rademacher's result. Even if you have one more edge, how how many you can have. There's a jump from 0 to linear, as we see there. So let me show you an example of this type of result. It has been studied before, we just phrase it this way. So a book of size Q basically is two triangles sharing one common edge. There's two triangles here, okay, by a book of size Q. And it was also conjectured by relation, proved by Ivanov and Nikiforov in 1979, that when you have one more edge than n squared over 4, then all of a sudden, the largest size of the book you can always guarantee in this family of graphs, namely in family graphs with this many edges, is n over 6. So from no triangle to all of a sudden, if you add one more edge, we necessarily guarantee n over 6 triangles sharing one same edge. So this is as you can consider it as earliest Rademacher type problem concerning the size of the book that you can always guarantee. Okay? So this is also a jump from 0 to linear. So let's get to the problem we're considering. So let me introduce these clique saturating edges. So for example, let me focus on 4. So the G be a K4 free graph. We always work with K4 free graphs with n squared over, we focus on K4 free graphs, and an edge in its complement, namely a non-edge, is called K4 saturating edge, if the addition of this edge creates a copy of K4. So originally the graph is K4 free, and you add an edge, you can create a K4. We call this non-edge K4 saturating edge. And the first external result related to clique saturating edge is by Belabovac in 1968. Well, just among others, he proved for if every edge in the complement of this graph G is a clique saturating edge, then the number of, we have a lower bound on the number of edges in this graph. And this best possible, consider, let me just draw the K4 case. You don't have to read this. So the K4 case is we draw an edge, and then only n over 2 vertices from an independent set and join all the edges in between. So as you can see, this graph has 2n minus 3 edges, only linearly many edges. But then every non-edge in this graph is in this independent set. Every non-edge, if you add it, you create a K4. So every non-edge is in a complement is a K4 saturating edge. Yet the graph only has linearly many edges. So to the other side of this spectrum, a graph, when you consider balanced bipartite graph, you could have up to quadratic many, all the way up to n squared over 4, but then no edges in a complement is a K4 saturating edge. Because no matter what non-edge you add, you only create a big book. That's it. We cannot get a K4. Okay? So let me define this parameter f, n comma e, depends on the order and the size of the graph, as the maximum integer L value that in any n vertex K4 free graph with e edges, you can always guarantee L saturating edges, K4 saturating edge. Namely, if we just look at all the family with this particular prescribed order and size, how many you can always guarantee K4 saturating edges? Okay, in K4 free graphs, of course. So this again, this complete bipartite graph shows that when we have this size, it's 0 because we cannot guarantee anything by this complete bipartite graph. So this is a conjecture by Ernest and Tuza in '83, I believe. They say if we have one more the size, namely if you consider the family of all K4 free graphs on n vertices with n squared over 4 plus 1 edges, then all of a sudden, from no K4 saturating edges you can guarantee to 1 plus below 1, roughly n squared over 16, quadratic many. So this jump from 0 to quadratic many. So this is their conjecture. And this is, again, early Rademacher type problem concerning the number of K4 saturating edges. Okay? And if this is true, then it should be best possible if this is true. So as in this case, it's not the most natural example that one would expect by adding one edge to have this one additional one, because if we add this one, what will happen is, can everyone want to see this example? What will happen is every non-edge on the left-hand side will be a K4 saturating edge, right? Together with this edge here. Then how many we create here? We create roughly n squared over 8. So this is weaker than this. This upper bound is not good enough. So their example is we're going to cut, roughly have n over 2 minus 1 and n over 2 here. We rip out one vertex, and adjacent, make it adjacent to half of the vertices on each side, okay? In order to have this one additional edge. So then, where does this, let me just put this part here, where does the K4 saturating edges lie in? It lies in these two parts that this vertex is adjacent to, right? Any edge here, together with this vertex and any vertex here, will create K4. Then now the calculation becomes n over 4 on each side, and if you do the calculation, it's roughly n squared over 16. So if it is true, this example, kind of intuitive, will show that it's best possible. And a quick thing here, a quick lower bound here, as I mentioned, the lower bound for the book here, n over 6, we can, yeah. So this, a big book guaranteed by this many edges will quickly imply about n squared over 72. Why is that so? If we have a big book of size n over 6, then as you might imagine, every non-edge up here is a K4 saturating edge. So n over 6 immediately gives you n squared over 72. So this is a weak lower bound implied by the previous results. So we disprove this conjecture, and we find this counterexample showing that we can only have this one give an upper bound of 2 over 33 n squared. So as you can see here, I partition it. It's blow up of the C5 with the chord, where the proportion is listed here. I have a plus and minus point here just to make sure we have one more edges than n squared. But as you can see here, we actually have linearly many edges above, additional edges above n squared. So here, all the K4 saturating edges lies in V1, V2, and V3. Right? Any non-edges varies. And just do some calculation, we can find out its ratio is 2 over 33. So furthermore, we prove also the matching lower bound, and prove that actually in any graph, if you have n vertices and n squared over 4 plus 1 edges, then we can always guarantee this much, 2 over 33 n squared. So this is best possible. The previous example we showed here, the blow up of C5 with the chord is best possible. This is the best we can hope for. We only guarantee this much, so equality. And just a remark here, we have only linear order term, linear order error term when they conjecture 1 plus below. Here. So we actually prove the following theorem, which implies the lower bound. We actually prove this theorem. If we consider n vertex graph, which is K4 free with n squared over 4 edges, so that plus 1 we use it in a way that necessarily by mental theorem, this n squared over 4 edge plus 1 edges, we will have a triangle. So using this way, we have this many edges and a triangle for n at least 73, and we can prove that the number, which I haven't divided here, f of g denotes the number of K4 saturating edges in the graph, in the complement, is at least 2n squared over 33 minus this linear term, which is best possible in this construction. So this, as you can see, will imply the previous result, because as I mentioned, Mentel theorem says we should have a triangle here.